everyone, this is 61BL Summer 21 Final, question 7. So in this question, we're given a disjoint sets interface that we have to implement. So we need to implement two functions that a disjoint set supports. It's called connect and is connected, right? Connect takes in two integers, p and q, and it essentially mimics this connect procedure that we saw in lab and in lecture. So if we're given two disjoint sets, meaning two sets without any common elements, right? So maybe I have one set like this, right? It has some elements, and one other set like that. It has some other element, right? If I just connect them, maybe I add like a bridge between them. These two should now become a bigger set together, right? So we're now doing something like that. So this is the idea behind using a disjoint set. If you're given two sets with no common elements and I call connect on them, they now form a bigger one singular set, okay? Is connected, we'll just check if two given elements belong to the same set or not, right? So in the first case, if P and Q belong to different sets, then they would not, then is connected if P and Q would return false. But if P and Q belong to the same set, right, is connected would return true, okay? So this is the idea. Cool. Now in lab and lecture, we saw that disjoint sets are usually implemented using union find. So we use parent operators, and then we use ranks and weighted quick unions and whatnot. But here we're trying to use a different implementation of disjoint sets. And here we're given a graph class that we will be using heavily to mimic this sort of disjoint sets data structure, okay? So we're given three functions for a graph. We're given addEdge, we're given adjacent, and we're given size. addEdge is just going to add two edges between given vertices. Adjacent is going to return the neighbors of a given vertex, and size is going to return the total number of vertices in the graph, okay? The only constraint that we have is our methods connect and is connected should not use more runtime than O of V. So at best, in the worst case, we don't want to do anything more than just iterating through all the vertices, right? So that's the idea. We don't want to do too much work, but we still want to use this disjoint sets representation, okay? So now the idea is, let's say that I have two sets that I choose to represent using graphs, right? So maybe I have a set with elements 1, 2, and 3, right? So this is just one set. And I have another set, 4 and 5, okay? This is just another disjoint set. And now, if I try to connect these two sets, right? Maybe I call connect of 3 and 4, I can simply just add an edge between 3 and 4, right? If I do something like this, now, technically, this is a graph, a singular graph of all 5 elements between the original two disjoint sets that I was given, right? And if I want to call is connected of, let's say, 2 and 5, right? Then I could simply start at 2 and maybe run a breadth first search process to go through each element that's reachable from 2, right? So if I follow all the edges, if I try to use breadth first search, I will start at 2. I'll visit 1 because that's at the next level. Then from 1, I would go to 3. From 3, I would go to 4. And from 4, I would go to 5, right? As soon as I reach 5, I would notice that, okay, so 5 is reachable from 2 because we were able to execute breadth first search and we were able to visit 5 in this process. That means that there is some path in our graph from 2 to 5, which means 2 and 5 are connected, right? So it would return true in this case. However, without this edge that I just added between 3 and 4, this edge is usually called a bridge. So without this bridge, if I executed breadth first search from 2, I would go to 1 and then to 3. But then from 3, I cannot go any further, right? Because there's no other edge to follow. There's no other vertex to visit. in this mini graph. And in this case, I will not be visiting 5 in the breadth first search process. So I will have to return false that 2 and 5 are not connected. Okay. So the idea again is whenever I see a procedure to connect two vertices or two elements in my set, in two different sets, then I can simply add an edge between them, right? And whenever I want to check if two elements are connected to each other, then I can just choose one of the elements and execute breadth first search to see if I visit the other element, right? If I visit the other element, they're connected. If I don't visit the other element in breadth first search, then they're not connected. Okay, and this is what we have to implement in this skeleton code that we're given. Okay, and because we're using breadth first search, we will also meet the runtime requirement because in breadth first search, we don't visit any vertex more than once, right? So that's the idea. Okay, so now we will look at the connect function. So if I want to connect two elements, P and Q, right? So let's say I have two elements here, P and Q, that belong to different sets. I can simply just add an edge between P and Q, and now I'm done, right? They're connected. However, if P and Q were not in different sets, so if they were in the same set, then I don't need to add a new edge between them because there's already some other path between P and Q that I can follow to check whether or not they're already connected, right? So in this case, there's no need to add a new edge, and we will avoid doing that as well, okay? So I would just check here if P and Q are not connected, right? Using my isConnected function. So if they're not already connected, then I can add a new edge between them, right? So I can say graph.addEdge of P comma Q. Okay. And if they are already connected, then I don't need to add an edge because they're already in the same graph in the same set. Then we don't need to do anything with edges here, right? So that's the idea behind the connect operation. And now for the isConnected operation, as we discussed before, we can just simply execute a breadth first search procedure, right? So if I had 1, 2, 3, and 4 that were all in the same graph, right? I could simply just execute breadth first search to check if 1 and 4 are connected, right? So if I called is connected between 1 and 4, I would first start my breadth first search procedure from 1. I would visit 2 first. 2 is not 4. I would visit 3 next. 3 is not 4. Then I would visit 4. And 4 is the same as the other element that we're given. So 4 is equal to 4. And I would immediately notice that, okay, 4 is reachable from 1. So they must be connected, right? So I will try to implement a breadth first search procedure here using a fringe that we're given in the form of a list and this while loop that I'm given. I'm not given anything else. That's all for this question. And yeah, so basically I notice now that for BFS, for breadth first search, we generally use queues, right? But here I'm given a list. So I will try to mimic the process that a queue performs, the functions that a queue supports of just adding to the end. So if I'm adding a new element, maybe I'm adding 4 to this list, right? And then for removing something, the queue would remove from the front, right? So I would just remove this first element from the list. So if I had just a queue of 1, 2, and 3, and I say q.add 4, it would add 4 to the end. And now if I said q.remove, then it would remove the 1 from this queue, right? So we're adding to one end and removing from the other end. And this structure is heavily used in breadth first search, just as we learned in lecture and lab. Okay. The other thing that I will need for this question is a visited array that we usually use, right? So a visited array is only used in order to ensure that we don't visit any vertex more than once. And that would also help us guarantee our runtime of O of V, right? So as I visit the vertices, I would mark them as visited in my array, and I would always check before visiting a new vertex so that I don't visit it more than once. Okay, so here I would just initialize a Boolean array called visited. Okay, and I would say new Boolean of, for the size of this array, I would just look at this size function that we're given that returns a total number of vertices in the graph, and I can simply just call that function to get the size of my visitor array as well. Okay. Cool. So that was that. We now have a visited array. And now in my while loop, I will just execute a breadth first search procedure to check if I can ever visit Q when I start BFS from P. Okay. So I've already added P to my fringe, which means I'm using a breadth first search process from P. And inside my while loop, I would always just say int n, so n for next, equals fringe.remove. But because this fringe is a list instead of a queue, I would just remove from the front. So I'll specify index 0. That would just remove the first element in the list, right? Specifying the index 0. So if this was index 0, 1, 2, and 3, fringe.remove of 0 would remove the 0th index of the list that I'm given, right? Which would basically mimic the same q.remove procedure that we usually use for BFS. Okay, so now I would have the next element that I need to visit. As I visit it, I will say visited of n equals true. And then I would want to see the neighbors of this element, right? Just as we normally do in vector search. So for the example that I just had, as soon as I visit 1, I would want to add 2, 3, and 4 to my fringe, right? Because they have not been visited yet. So I visited 1, and now I want to add 2, 3, and 4. So for here, I would just say for, I have another function that I'm given called adjacent, right? And adjacent returns to me all the vertices adjacent to a vertex V, which basically means all the neighbors of V, right? So I would just do for integer neighbor of in graph.adjacent V. So now I'm basically iterating through each neighbor. And here I would check if the neighbor has not already been visited. So if not visited of neighbor, then I should be visiting it. So I will just add it to the fringe. Fringe.add neighbor. Okay, cool. And one more thing that I need is as every time I visit a new vertex, I should just briefly check if n is the same as q. So if the current node that I'm visiting is the same as my destination, which would happen when we visit 4, then we can just return true, right? Because that means that I was able to visit 4 from 1 when I executed breadth first search, right? So if ever I visit a vertex that's the same as my destination, that the vertex that I'm trying to reach, then I'm done, right? That means that they're already connected. So the isConnected function should return true. And otherwise, at the end of my function, I can just return false because that means that I visited all of my vertices in the fringe, and I tried to visit all of the neighbors, but I was never able to find the queue that I was given, right? I was never able to find 4 in this case if this edge did not exist, right? So if I'm not able to visit 4, at the end, I should just return false. Again, just to confirm, at best, we are visiting all of the vertices in the graph, right? Because this visited array keeps checking if the neighbor is not already visited, and then and only then does it add a new vertex to the fringe, right? Or an element to the fringe. So because of this visited array, we're not visiting a vertex in our graph more than once, and that guarantees us or v runtime.